All right, everyone, so this is going to be the video that covers pretty much all of the graphs we're going to experience within this unit. I'm not talking about bar graphs, I'm talking about actual graphs that, graph real data points as time goes on. So since we started this unit with conservation of momentum, we're going to start by looking at the graphs that we might see that help us represent conservation of momentum. Now, I've already talked about those weird bar graphs with velocity and mass where the area is the momentum. Those are not the graphs that I'm talking about. Those are just great ways to visualize what's happening. With these graphs, we're actually, like I said earlier, going to be graphing real data. So let's say that I have a block of mass m moving to the right at a speed 2v, and then a block of mass 3m moving to the left at a speed v. And then after the collision, we have a block m is moving to the right at v. And I can kind of quickly figure out what speed the 3m block is moving by doing just some quick conservation of momentum calculation. So m times 2v plus 3m times negative v has to equal m times negative v. That's a v, not an m, plus 3m and some unknown speed. So it's 2mv minus 3mv is negative mv plus 3mx. mv is negative mv. And then when I add this to both sides, I get 0 here. So what that means is the 3m block actually comes to a stop in this collision. Okay? Now I can represent the momentum and the velocity of this system as time goes on. Okay, so I have this grid here, which I'm going to graph on. I'm going to zoom in a little bit. So if I wanted to graph the momentum as time went on, I would need to make sure that I have both a positive and a negative side of the axis, since momentum is a vector and it can go in both directions. And what you'll usually see is we'll kind of have like 3 different sections to this graph. Kind of like when we did that force versus time graph for the collision, we had like a before, a during, and an after. Now, the during right now looks like it happens over a long amount of time. In reality, the collision occurs very quickly, but we're going to kind of extend or expand or exaggerate that during part so we can kind of see some cool things that happen with the graph. Okay, so let me switch colors so I can kind of see a little bit easier. So before, we have one object that has a momentum of 2mv and another object that has a momentum of negative 3mv. So I have, let's see, a 2mv and a negative 3mv. And then after the collision, this 3mv, that's the 3m mass, that goes to a rest, so it goes like that. And then the 2mv has a momentum of mv afterwards. So I usually do my befores and my afters, and then I connect them. So this connects like that, and that connects like that. Okay. Now we might notice some things about this graph, specifically in this during section. Okay? So take a few minutes, maybe pause the video to kind of look at these 2 lines and think about some things that you notice. How do those lines compare to each other? What do they look like? And so on and so forth. So what we might notice is, what do we notice? Okay, we might notice that during the collision, the slopes are equal in magnitude, meaning their number is the same, but they are in opposite directions. Okay. For instance, this line has a rise of 3 and a run of 4, and this line has a rise of -3 and a run of 4. So our slopes are equal and opposite. Now this makes sense because we know that in a collision, the force between A and B is equal and opposite to the force of B on A. And we've shown many times that the consequence, or the effect of that, is that the change in momentum of A is equal and opposite to the change in momentum of B. And that's really what that slope represents, is that change in momentum as time goes on. So it makes sense that these changes in momentum are equal. Okay? And it makes sense that beforehand we have no slope because our momentum isn't changing. We're traveling at a constant velocity. So let's talk some more about what that slope might represent. We know that anytime we calculate a slope, it's a change in y over a change in x. So here, change in momentum over time. Well, change in momentum is really mass times change in velocity over time. What's velocity over time? Oh, well, that's acceleration. What's mass times acceleration? Well, it's a net force. Okay, so again, kind of makes sense that these slopes are equal and opposite because we know the forces are equal and opposite. And these forces are what's represented by the slopes here. And again, makes sense that our slopes are 0 here. If we're traveling at a constant velocity, we have no net force. So everything kind of supports each other and builds off of what we already know. So that's one way that I could represent this kind of conservation of momentum collision. Another way I could, and I just got to go grab another grid. Another way that I could represent this is a graph that we are familiar with. And that's going to be a velocity versus time graph. Now, like momentum, velocity is a vector, so I should have a positive and a negative. So here, initially, I have one object that's moving at 2v. I should probably make my before, during, and after. Before, during, after. So I have my block of mass m, which is moving at 2v. And to kind of make my graph a little bit bigger, I'll say that 2v is up here. And then my 3m mass is moving at a -v. And then after the collision, this object moves at -v. So I can kind of connect them like that. And then this object comes to a stop. Okay. So again, pause for a little bit of time and think about what you notice in this graph. Do we notice the same sort of things? If not, if why, you get what I'm trying to say. So hopefully you paused, and one big difference that I see is that here the slopes are not equal. Okay? And that's important for us to realize because remember, on a velocity versus time graph, the slope equals the acceleration. And even though the forces between these two objects might be equal and opposite, they do have different masses, which means, oops, there should be negative. They are going to have different accelerations, right? We see that the more massive block has a smaller magnitude slope or less steep slope, meaning less acceleration, which we would expect. And the smaller mass, feeling the same force, has a greater acceleration, just in the opposite direction. So here the slopes are not equal. Some things to keep in mind when graphing these conservation of momentum things is when two objects stick or start together, they have the same velocity. So this velocity versus time graph, the two lines will overlap each other if they're traveling at the same speed, but not necessarily the same momentum. Right? Like if we have two objects traveling at the same speed, but they have different masses, then these momentum graphs will not overlap like we might expect. Okay, so just kind of like quickly sketching something out. If I have one object moving like this and a bigger object moving like that, and then maybe after the collision, they move together to the left, my velocity versus time graph would look something probably like this, right? Like that. But my momentum versus time graph would, let's see, this would be here. This would be that, oops. And then this might be like here. This one might be like here, right? They're not going to have the same momentum after, right? This bottom line is representative of that larger mass, so it has a larger negative momentum, but I tried to make these slopes still look the same, right? And again, here I tried to make this slope for the more massive object less than this one. So just make sure you're paying attention to what is on the y-axis. Is it momentum or velocity? It does throw students off sometimes. All right, so the next kind of graphs we're going to look at is our non-conservation questions, or our impulse, and change in momentum. Okay. So we know that the impulse of an object, or the change in momentum, is found by applying a force over a specific amount of time. And this equation works as long as the force is constant. Okay. Much like the work equation, right? That work equation worked as long as the force was constant. If our force is changing as time goes on, then we need a different way to find the impulse. So, of course, what we're going to do is we're going to graph the force as a function of time. So maybe our graph looks something like this. Okay. So here in this equation, force and time are multiplied. And when I'm graphing force and time, and when I multiply force and time, that usually gives me a good hint that the area of this graph is going to represent the change in momentum or the impulse. So that's actually what's going to happen. We're going to say that the area of a force versus time graph is change in momentum or impulse. Okay. So if I wanted to find the change in momentum of this object, what I would do is I would split this up into a bunch of right triangles, and I would calculate, this area, and I would calculate this area, and both of those areas would be considered positive, which means I'm adding momentum to the system, or I have momentum to the right, and then both of these areas would be negative. Okay. Now, I'm going to assume that my object is initially moving to the right when this force is acting, right? So I'm initially moving to the right, and then I have this force acting. So what that means is my object is speeding up here, and it's still speeding up even though my force is decreasing, because I still have positive area here, right? Positive change in momentum, so I must be speeding up. I don't start slowing down until my force flips directions and opposite the direction that I'm moving. Okay, so what I could do is I could add up all those individual areas and kind of get like my total impulse. Remember, J is the letter for impulse, and I could set that equal to the change in momentum, which is really mass times final velocity minus initial velocity. And make sure you're paying attention to the fact that this initial velocity is not always zero. That is one thing that throws some students off sometimes. Okay, so that's force versus time graphs. We're going to look at the area to get change in momentum. Okay. Another graph that we've already talked about, but can kind of talk about again, is that if we have a momentum versus time graph and we see some sort of line that is not horizontal, some sort of diagonal line, right? This quite literally means that there is a change in momentum because our momentum is not constant. So that means there must be an impulse. And we've already talked about for these graphs how the slope equals the net force acting on the object. So if I wanted to find the net force acting on the object, I could find the slope. And if I wanted to find the change in momentum, then I would just find the change in y values. Now, the last thing we're going to talk about is kind of like collision problems where momentum is not conserved. Actually, let me grab a grid for this one. So, there's a grid. Okay, so these graphs are just easier on grids, we will say. Okay, so if I have, so in a question, we might be presented with a momentum versus time graph that represents a collision of an object. We might have an object that starts with this momentum and then has this momentum, and this ends moving like this, and then this one ends moving like this, and that connects. Or maybe we don't know what the center looks like, right? But in a situation like this, my initial momentum is negative mv, and my final momentum, maybe sometime after the collision, is 0. So this tells me that there's some sort of force exerted on the objects other than the forces that are in the interaction, which is why our slopes are not equal, right? There's some other external force causing not equal slopes, right? So this would be a situation where momentum appears to not be conserved. Our total momentum has changed, right? Initially, my momentum, like if this is mv, or 2 mv, and this is 3 mv, right? My initial momentum is negative mv, but then my final momentum is 0. So clearly there's some other force that has acted. So this might be an example where maybe our collision took place on an incline. So, maybe we had a heavier object moving uphill and then a lighter object moving downhill, and they collided in such a way that just after the collision, they're at rest, right? So this tells me that because their momentum changed, there must be some other external force creating non-equal slopes. And in that case, that external force would be, there could be friction on this incline, but there also, remember, is a component of gravity pointing down the incline, changing the overall or total momentum of the system. Okay. Now, this graph doesn't come up that often, so if this part kind of confused you, totally okay. The important part here is this force versus time graph, and remembering that the area is change in momentum. Okay. All right, so those are all the graphs of real data that we might see in this unit.